So it is recording because I accidentally showed a piece of the grade sheet in the other class, so I had to cancel that recording. Let's see. We are doing 3.6a today, 6 quick problems, but I need for you to make sure you've got those done before Wednesday, because when we do 3.6b, 3.6a is going to make a ton more sense, or sorry, 3.6b will make sense because you'll understand 3.6a. It's really easy, really short, very little to learn. We're also going to do 3.5 today, which we will probably get almost finished. That isn't as important to get done by Wednesday. If you don't get that done by Wednesday, that's okay. But 3.6a would be great. This is our test distribution, 17 A's, etc. The average was 83. That was a tad lower than last time. So, you know, everything's going fine. If you made an A or a B on this test, you're doing what you need to do. If you made lower than that, you might think about, you know, the way you learn and doing something different. I will open up all of my math lab, all of the last 2 tests, all of these sections later on this week, so that you'll have spring break to work on them. Of the 34 of you, there are 34 people that have taken the test, 34 of you, 16 of you have perfect my math labs. That's half of you, one shy of half of you. So we'll round, we'll call that half. Half of you are playing the game exactly the way I believe the game needs to be played to get out of here, maximizing every point that you can on your time. A lot of you, 18 of you, half of you are not perfect, but of those 18, 13 of you still have A's. Only 5 of you don't have A's in my math lab. So a class of 34, a couple classes, 34 people, 5 out of 34 don't have A's on their math lab. That's incredible. You guys are not only, you're taking care of business on your end, you're doing what you have to do to get out of this class successfully in May, so you're not stuck taking it again. You're just doing what you need to do, and I'm thrilled by that. I think that we've all kind of figured out a way to make this successful, or at least the group that's together now has figured out how to make this successful in a coronavirus semester. Don't want that for fall, though. That has nothing to do with your My Math Lab section. Okay, let's move forward. Let's look at 3.6a. All of these will be called solve. They're polynomial inequalities. That means we're going to have less thans and greater thans happening. They're going to start with one that's already factored for you, something like that. X minus 4 times x plus 1 is greater than 0. We're still looking for the 2 numbers over here. So x minus 4 equals 0, x plus 1 equals 0. You know that that is not telling the truth, that we're going to do the opposite of when it's associated with the x. Move it over, it becomes -1. Same thing here, x minus 4, move it over, it becomes x equals 4. So these are our 2 goalposts. If this were an equal sign, that would mean that 4 and -1 would work and give us 0. But we want all of the numbers, and there's going to be a great vast quantity of numbers that are greater than 0, not just these 2. So let's put them on a number line and see where they are. There's -1 relative to 4. This arrow points us outside. That's greater than. We want where the numbers are great, where they're big numbers. That's out here. It's also over here. They have negatives in front of them, but still they're great big numbers. It does not say or equal to, so we need to not include those numbers. And that's the answer in interval notation. -infinity to -1, union 4 on out to infinity. It says that any of these numbers will work in this equation, in this inequality. Like the number 5. 5 minus 4 gives us 1. 5 plus 1 gives us 6. 1 times 6, that's a positive number. It's bigger than 0. So that's why I shaded over there. Let's find a number in here that won't work. Let's say 2. 2 is in that gap. 2 minus 4 is a -2. 2 plus 1 is 3. A negative times a positive will give us a negative, and a negative is not bigger than 0. So that's why this piece isn't shaded. We're not going to go through that process on every one of these. but I want you to know that you can. You can look and see, pick a number in each one of those intervals and plug it in and see what works and what doesn't work. But I think it's a lot easier when you have a greater than to grab the outsides. You're going to shade the outsides. Similarly, if we have a less than, we're going to shade the inside between the two numbers, and we'll look at that in this very next problem. So we have 6 problems. There's number 1. Let's look at number 2. X squared minus 7x plus 6 is less than or equal to 0. Factor this side. X and x, the signs need to be the same and they'll need to be negatives. What 2 numbers multiply to give you 6 that add together to give you 7? That's 6 and 1. It doesn't matter what order they go in. Move them over. So we get x equals 6 and x equals 1. Let's put that on a number line. And then it says we want to grab the numbers that are less than. The numbers that are less than will be inside, in between our 2 goalposts. So there is where our answers are. This says or equal to. So that means we can use 1 as a possible answer. We can use 6 as an answer. So in interval notation, you get 1 to 6, including those 2 numbers. For instance, let's say we use 6. 6 minus 6 will give you 0. 6 minus 1 will give you 5. 0 times 5 will give you 0. And 0 is less than or equal. It's equal to, but it's one of those things. It's either less than or it's equal to 0. So that's why that 6 is allowed. Same reason why the 1 is allowed. And because it's less than, we want to go after the little part of the number line, not the greater parts of the number line. If it says greater than, it's pointing you to the outsides, we'll use the outsides. If it points you to the inside, you use the inside, the littler part. Let's look at number 3. X squared minus 24x plus 144 is less than 0. Again, factor. X and x, signs need to be the same and they need to be negative. What multiplies to give you 144 that adds together to give you 24? That's a perfect square, 12 times 12, and sure enough, 12 plus 12 gives you 24. So we've got x minus 12 equals 0 twice. So x equals 12 twice. Okay, let's see what that's going to look like. We want to shade the numbers that are between, we want to shade the part of the number line that is on the inside between 12 and 12. Well, there is no number on the inside between 12 and 12. So the answer here is the null set. There is no answer that's going to work in here. 0, if we put 0 in, 0 squared, 24, 0, 144, that is less than 0. Oh, sorry, I meant 12. The number that was trying to be our answer, 12 squared minus 24 times 12 plus 144. With this side would give us 0. And 0 is not less than 0. So we have the null set. There is no number between 12 and 12 that we can shade. That's the only weird one that's going to happen to you, the one you have to think about. The rest are just going to be very much like 1 and 2. 3x squared plus 7x is greater than or equal to 0 is number 4. We're factoring. We have an x squared term, we have an x term, we don't have a number term. So that is not going to factor into 2 sets of parentheses. This is only a GCF problem. I see I've got an x that I can factor out of both terms. So let's see, x equals 0, that's easy enough. 3x plus 7 equals 0. So I'm going to have 0 on my number line. But this one I need to solve. Move the 7 over, it turns into a negative 7, and then divide by 3. So we get negative 7/3. It's on the negative side. You don't care where that is. You don't have to worry about, oh my gosh, I got to turn that into a mixed number, because all we care about is, are we graphing the outsides or the insides? Where are the good answers? Greater than means you're going to go to the outsides. When it's greater than, you're going where the numbers are great, where the greater than numbers are, both sides. And then this says or equal to, so we're able to use the numbers themselves. And in interval notation, negative infinity to negative 7/3, union 0 to infinity. Number 5, got, something I want to show you here on the ones we've got. This is yes, that works. That doesn't work, that does work. It's yes, no, yes, alternating. Same thing here, no, yes, no, that's alternating. This one doesn't count. This one alternating, on, off, on. That's what's going to happen in 5 and 6 also. Yes. Greater than is the outsides. This was a greater than, so we shaded the outsides. This is a greater than, so we shaded the outsides. This is a less than, so we shaded the insides. Yes, if it's less than, it's inside. If it's greater than, it's outsides. Okay, this one's already factored for us. Already factored for us. X equals 0, 2 minus x equals 0, and x minus 8 equals 0. We got 3 goalposts now. Let's see what we're going to do with that. The easiest way to get x by itself is just to move him over. So x equals 2, and then move that 8 over. So here are numbers, 0, 2, and 8. Okay. Now, this says less than, and that means shade the insides, but we've got a lot of insides. It's hard to tell what's insides here. So we're going to have to do a checkpoint. We're going to have to do one checkpoint. I am going to, we've got a big gap here. I'm just going to check 5 to see. I'm going to see what's going on with 5. He's not a goalpost. That's why I stuck him up here so I don't get him mixed up. I only have these 3 goalposts. We're still going to do yes, no, but we got to find out where one segment, if it's a yes or a no. So let's check on 5. That'll give us 5 times 2 minus 5 is negative 3. 5 minus 8 is negative 3, and it's less than or equal to 0. This is a positive times a negative times a negative. So that's going to be a positive. It happens to be a 45. We don't care. It's positive. Is a positive less than 0? No. So that means this interval where I selected my 5 is a no-go. It does not work right there. So this will work. This will not work. This one will work. And this one will not work. So it's got a yes, no, alternating thing going on. So we just had to check 1 to see on that. I picked the 5, Austin, because I needed to get a checkpoint. I could have picked 1. I could have picked negative 17. I could have picked 35. I just have to pick a number from some gap in here and test it. Because I know it's going to be, I'm supposed to shade the insides, but you know, what's inside when you've got 3 different ones? You can't tell that when you've got 3 goalposts as opposed to 2. So you just do a checkpoint. I checked 5 and found out, 5 didn't work. We could have checked 1. We would have found out 1 did work. That's a positive times a negative. That'll give me a negative. A negative is less than 0, so 1 would work. And we'd shade there. Nope, yep, nope, yep. So we just took it as a checkpoint. Well, we're not there yet, Jackie.
When you were checking for the 5, where did you get the negative 3 and the negative 3 from to check it?
I plugged it in here. So it says 5, so I put a 5. It says X, so I put a 5. It says X, so I did 2 minus 5. That gives me negative 3. And then 5 minus 8, because it's X minus 8, and I'm checking 5, so that's a negative 3. I just plugged it into the original problem.
Oh, okay, see. Thank you.
You're welcome. Okay, so it says equal to, so we got to put brackets here all over the place. And then our answer, going left to right, we've got 0 to 2, union 8 on out to infinity. Okay. Anybody still have a question on 5? Holler if you do. Okay. Let's look at number 6 and be done with this section. see, we've got x to the third. We get 8 to infinity again. You mean, how did I know that one would work? That segment would work? Is that what you're asking? Okay, because this one did not. So if this is a big fat no here, I know that they're going to go in order, light on, light off, or yes, no, yes, no. So if this one did not work, this segment has to be a yes, that segment has to be a yes, and this segment has to be a no. It's got to alternate. Does that make some sense or not? If it doesn't, tell the truth. You're welcome. And I would pronounce your name only when I met you. I pronounced your name after you said it, and you laughed at me because it didn't sound like your native language, because my mouth doesn't do what yours does. So I'm not even going to try. And I can't run. I've got a Vietnamese friend at work, and I don't get to see him anymore. Yes, Chloe, you can test a number. You can, if you're asking, you can test any number you want to. What do you mean by that? Okay, if you, maybe you're typing, there you go. Let's see, I just mean that I could test numbers. Yes, absolutely. Yes, you can test any number along there. So if you had grabbed a negative number, and I know all of you are eager to play with negative numbers, but if you'd grabbed a negative number, it would not have worked either, because that's in the no section. If you had grabbed 1 times 1 times negative will give you a negative. That would have worked. You would have gotten a number smaller than 0. So you would have known this worked. And once you know one segment works, once you find one answer, then you know it's, tails, heads, tails, or yes, no, going along the string there. So once you find one of them, you know all of the others. Okay, let's look at number 6. Minus 6x squared minus 36x. There we go. Okay, this one was factored, this one is not. We're going to have 3 goalposts in this one, just like we did in number 5. 4 terms, so I know I'm going to factor by grouping. I can pull out an x squared out of these. Look at how often we factor in this class. This class is a class that relies on your knowledge of factoring. Bring down the minus sign. You know that this piece needs to also be x minus 6. What do these have to have in common? They better have a 36 in common. Then I'm looking at that piece, and I will pull out an x minus 6. X squared minus 36 is the rest of the business. I can still factor this. This will factor into x plus 6, x minus 6, equal, doesn't matter. We're going to decide what to do with that later, so it doesn't matter what that equality or inequality says. This gives me x equals 6, x gives me negative 6, and gives me another 6. So on a number line, we got negative 6, we got 6. We got 2 6s here, so we have the same problem. We really have 3 roots, so we're going to have to test. We're going to have to do a checkpoint again. Let's check 0. So let me make a note to myself. I am checking 0 here. I just picked a number. You can pick any number you would like to. Any number will do, just to get a gauge of which one of these is going to work. So let's test 0. 0 cubed, 0 squared, 0. We get 216. So when we check 0, 216 is greater than 0. Yeah, that'll work. That makes a true statement. So we know that all the numbers in that gap work. Now, here's the problem. We're guaranteed of this. We're not, because this is no yes, but this is where the double thing happened. So we're going to have to test this also. So let's try 10. Let's check 10. Let's do it down here. That's going to be the easiest place right here. 10 minus 6 is 4. 10 plus 6 is 16. 10 minus 6 is 4. That's a positive number. A positive number is greater than 0. Yeah, that worked there also. So this is also part of our answer. And that's weird because we have a double 6. So if you have a double number, you have to check both sides of him. If we did a billion of these, you'd get so good at this. But, you know, we're only doing 6 total, and only one of them is going to have a double number. So let's see, we do not have an or equal to. So we've got -6 on out to infinity is our answer there. Now, that's what you have to do. If your plate is full in this class, if you are, you know, feeling stressed enough about this class or life in general, then close your ears for about 2 minutes. But anybody who is willing to listen, I want to show you how this dovetails with something you already know. But it can't equal 6. That's correct. Can't equal 6. Oh, no, it can equal 6. No, it can't. You're right. Holy crap, Rebecca. How did you think of that? Are you just because you're smart and you're thinking about things outside the box? I'll take that as a humble yes. Yeah, Rebecca's absolutely right, and I'm not sure how I missed that one, but I did. I missed it at 8 a.m. and I missed it now. If it is 6, let's say it's 6. We've got put in a 6. Well, here's this place. 6 minus 6, that gives us a 0. 6 plus 6 gives us a 12. 6 minus 6 gives us a 0, and our statement's got to be greater than 0. 0 is not greater than 0. So we have a hole right there. We're going to have a hole right there. So this is a wrong answer. -6 on out to 6, use parentheses because it can't equal, union 6 on out to infinity is going to be the answer. We've got to leave 6 blank there. We've got to, what it looks like for us is like that. Absolutely. I'm going to have to go back and look at that problem in my math lab and figure out how I missed that piece of it, because I did. Okay, what I want to show you is what I was saying to you. If your plate is full here, Rebecca, you have to listen because your plate's not full. You're getting things that just aren't occurring to me, which is kind of embarrassing. Let's see. So wait, check to show x is equal to 0. Which won't work? Yes, we checked. When you check 6, it will not work. Numbers over here will. The problem is that this does not say or equal to. If it said or equal to, we'd go screaming through 6. But it says it's got to be greater than. So, and you know, if we do, good. If we do 6 problems and 4 of them look one way and 1 of them looks a different way, figure out which ones you're going to have on your test. I mean, I'm not giving you weird stuff on your test. You already know that. You can trust me on that. But do use your notes. Okay, let me show you what I was going to show you. This problem is x to the 2nd power here. X times x is x squared. You know that's a parabola. So if we were to put that parabola in, it would look like that. And we are looking for where the greater area is. If you're comparing inside the bucket on a graph to outside the bucket on a graph, you know that outside the bucket is going to be bigger than inside the bucket. So in a 2-dimensional world, if we were to add in our y-axis, then we would be shading all of this outside here, not just the number line. This problem is not about the 2 axes. It's only about the number line, but I just wanted to show you that this fits with what you guys already know. Here, we've got an x squared. It's a parabola. It's facing up. And so this one would look like this. It's got to be less than. What's less than of the 2 regions we've blocked off, inside the bucket or outside the bucket? Inside the bucket is less of an area. That's why we're shading in here in a 2-dimensional system, or 1-dimensional system, just the x-axis, not the 2-dimensional system. The blue, again, if this is too much for your brain, just shut me down for a couple minutes till I pull this paper away. But I just want to show you how this works. I think it's very cool, but I get it that some of you may just be like, oh, can't do that, so ignore. X squared, we've got a parabola, but the parabola is going to sit right there using up none of the x-axis. It doesn't say or equal to, so it's not going to include that piece. If we were drawing this as a parabola, we would be doing dashed there, but we're not doing that. Later. So that uses up none of the x-axis. Here, X squared, it's a parabola, so it's looking like that. It says greater than, and sure enough, you're shading on a two-dimensional system, you're shading the outside where the greater than is. Oh, this is where the stuff gets good. Three-dimensional. You know what that looks like. That looks like snake armor. However, this has a negative x. X times negative x times a positive x. So we'll be coming in from there and going out here. Each one of these is a crossing place because it only hits once. So we're doing that, and then that, and then on out. And we are shading up here. See, if we're two-dimensional, we're shading up here, and that's what hits that part of the one-dimensional and that part of the one-dimensional. If we don't shade below, we never hit down there. And this is really the best one. 6, we hit twice. You know, that's a turnaround. So this is an x cubed. It's positive. So we're going to be coming in down there, going out there. At 6, negative 6, that's what we come to first. We're crossing through, and then we're going to bounce off of there. And that's why this one is a greater than. We're doing down here. Turn off my phone. Doing down here in a two-dimensional system. This does not say or equal to. No, ours are always equal to's because we do solid lines, but not here. This would be, as Rebecca discovered, this would be a not equal to, and it could not hit there, hence leaving out that 0 part. If I find out that this is wrong, I will send out an email to you guys and let you know. Or you know what? I'll just wait till Wednesday. Wednesday's right around the corner. Okay, let us proceed with our worksheet. Okay, 3.5. This first sheet that we have here will be a reference that we will use as we go. Too many definitions for us to attack all at the same time. You don't have reference for them yet. So I will continue to bring this back up to you and show you where the definitions are that we need. Let's jump into this. Number 1, you need nothing here. This is what is the domain. Remember, you have 2 aspects that you have to worry about in the domain. The first aspect is it in the denominator? The second aspect is it under the radical? These are all in the denominator, no radical. They're asking you to set your answer up as set notation, the set of all x such that x cannot equal. We're not going to do interval notation on these 3. So let's see. If we set x equal to 0, x cannot be 3. That's one of our bad numbers. And x cannot be negative 6. So your answer will be the set of x such that x cannot equal 3 or negative 6. Close it out and you're done. Just what can the domain not be? Any number in the world is good except the things that will zero out the denominator. You had a test question like that, I believe. Let's look at the next one. Again, we're looking at what can we put in for the domain. Anything that will not zero out the denominator. If you factor the denominator, you get that. Those are a problem, children. That's a negative 5. That's a 5. Those are problems. So the set of all x such that x cannot equal those 2 numbers, and you're done. Okay. This one, if we set this equal to 0 to find our bad guys, we get x squared equals negative 1. Take the square root, gives you x equals. Take the square root there, and you've got a non-real number, an imaginary number. So that tells us that we don't have to worry about that. We have no numbers we can't use. We're allowed to use everything in the domain. So in this particular section, they're going to call that there are no restrictions. Okay? There are no restrictions on the domain. Any number will work. Any number you can, there's no number in the world you can put in there for that x and have that equal 0. So the only problem we have to worry about, don't make the denominator be 0, is not something you can do with a real number. So no restrictions. Okay, let's look at number 2. What are the vertical asymptotes? Vertical asymptotes, VA is what we're going to abbreviate that. Don't forget about holes too. We'll worry about that in a minute. Let's look at vertical asymptotes. After possibly simplifying the function through factoring, okay, we're going to worry about that on these two, but not these two. So we'll start out with ones we can't factor. Set the bottom equal to 0. That's how we will identify the vertical asymptotes. So can we factor it? No. Let's set the denominator equal to 0, just like you were doing in number 1, exactly like you were doing in number 1. So we've got an x equals 0, and we've got an x minus 8 equals 0, which gives us x equals 8. Those right there are our vertical asymptotes. I know you don't know what one is, or most of you don't know what one is, so just hang on. This is the answer they want. They don't want 0, 8. If you don't put in x equals 0, they won't give you credit for it. So don't forget that. Okay, let's look at what an asymptote is. When we go to graph these, and we're going to graph number 7, number 8, number 9, and number 10 on this exercise, on this set of worksheets, when we do that, we're first going to look, the first thing we're going to look at is the vertical asymptotes. We have a vertical asymptote at 0. That means I'm going to draw a dash line there, and one at 8. I'm going to draw a dash line there. That means that our graph can play around all it wants to over here. It can play around all it wants to over here. It can play around in here. It cannot cross that wall. That is a brick wall. It's sort of like piecewise definition, but not really. It will never get to that wall. We will have graphs that will do things like this. They'll go sliding along here, ooh, go closer, 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 closer to 0 on this y-axis, or closer, closer, closer to 0 on the x-axis. And as they do, they're going down, 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 down to negative infinity. Will never, ever, ever cross that asymptote. Asymptotes, both vertical and horizontal, are walls that you can't get past. And we'll play with that. You will not have any trouble understanding what that is in an hour. Okay? What are the vertical asymptotes? Set the denominator equal to 0. That's what you're going to do. The denominator equals 0 when you're looking for vertical asymptotes. Okay, x squared plus 9 is like the third one up above, where there's no way we can make this be 0. You know, x squared equals negative 9. Take the square root. We've got imaginary numbers. So there is no real number problem. There is no number you can put in there for x that will give you a 0 for the denominator. So we call this no, and then a new word, discontinuities. It doesn't discontinue. No discontinuities. You don't have to know how to spell it. You just need to be able to find it in the, in the little circles on my math lab. So there is no restriction here. There will be no vertical asymptotes. There will be no walls where this one has to not continue. It has to stand up and start again. Okay, these two will be factorable, and we'll have some holes. Let's look at what that means. Let's factor this. That gives us x plus 12, x minus 12. So if we were doing normal, factor and cancel, we would cancel the x minus 12s, and we'd end up with 1 over x plus 12. That would be our final factored answer. So from that, we would set that equal to 0. We would know that one vertical asymptote would be x equals, move it over, negative 12. That's our vertical asymptote. However, the original problem still has a 0 in it. It has a problem at regular 12, at positive 12, and that's where our hole will be. Hole at 12, or hole at x equals 12. I think it's just 12. Hole at 12. So let's talk about what that means. Oh, very good example right here of a hole. There's a hole right there where Rebecca found that hole at 6, because it doesn't say it can equal it. So we're going to have to put a hole there. We can go awfully close to it, 5.999999 infinitely, and we can pick it up on the other end, 6.00000001, but not at 6. So there's a hole, what they're talking about when they say a hole. The vertical asymptote for this, though, is negative 12. So let's say negative 12 is there and 12 is there. We will have the vertical asymptote there. But whatever this thing does, if it does something like this, we'll just put a little circle there. That kind of thing. Because if you were to try x is 12, you put it in there, even though we've crossed it out, if you put it into the original, 12 squared is 144. 144 minus 144, the whole dang thing blows up. So when we cancel, we're left with the vertical asymptote in the bottom, set it equal to 0, just like we've been doing on all this page. But then whatever you've canceled out, that's where holes will be. Okay, let's look at this one. Second example. Factor this. X and x.
Why did you
Signs need.
cancel out the x minus 12?
Why did I cancel those two out?
Oh, never mind, I see it. Sorry.
Okay, and we're going to do it again here. Let's see, I think that was probably Kaylina, but let me check. Oh, you've already gotten rid of your, but yeah, I think that was Kaylina. So anyway, whoever it was, if it was Austin, although it didn't sound like Austin.
No, that was me.
Okay, we're canceling it because of the numerator. We'll be doing that here also. So we've got, need both signs to be the same and they need to be negative. What two numbers multiply to give you 72 that add together to give you 17? That'll be 9 and 8. Now, in continuing, I wrote this wrong. That's a minus. This should be a minus. Just copied it down wrong. And then continuing, we would factor these by canceling the numerator and the denominator and end up with 1 over x minus 8. Now's the time to look for vertical asymptotes. And we're looking for vertical asymptotes by setting the denominator equal to 0. So the vertical asymptote will be x equals 8. Move it across. X equals 8. But look back at the original problem. It had another x. It had another 0. It had another x-intercept. It had another solution, 9. So we also have a hole at 9. So on a number line, or on a Cartesian coordinate system, if we had our vertical asymptote sitting here at 8, there's 8. No, not necessarily equal part of the numerator for sure. Part of it for sure. But there could have been another piece up here, for instance, could have been like that. So you wouldn't know which one until you actually did the factoring. It just depends. We're only going to do one of those that factors, I think. So it's not, you know, it's just, this is a whole gobbledygook of stuff. And it's complicated, or it's a lot of steps, I guess. But you don't have a lot of emphasis on it. Little parts, yes. Always the number you cancel out. No, not necessarily, because like Austin was asking, if we had, did you mean this one up here in the numerator, Chloe? In the bottom. Yeah, it's always the one you canceled out. Yes, it'll always be the one you canceled out down on bottom, because it still lives inside this quadratic. We just got rid of it prematurely. Okay, so let's see. Here's 9. There's our fiddly-dee. Start over. Here's 8. Here's 9. We have got a vertical asymptote at 8. So there's a wall you can't penetrate. And so if we had something looking like this, it would have to take a break at 9. We have a hole at 9 where this problem doesn't exist at 9. Plug it in there. 81 minus 17 times 9 plus 72 will give you a 0 down there. And that, my friends, is bad news. Shouldn't it be -9? Crap if it's -9. No, ha ha ha, you're wrong. You know, I'm just kidding. That's x minus 9, because this says both signs have to be negative. So this, when you move it across, will be a +9. I'm glad you didn't get me twice there, Rebecca. Do you understand why it's a positive? Okay, good. All right, let's move on. We will play this game again in 7, 8, 9, and 10. Let's look at horizontal asymptotes. Horizontal asymptotes, the math isn't hard, it's just weird. Let's look at it. When you're doing horizontal asymptotes, you're comparing the exponent, the largest exponent of the top to the bottom. If the degree of the top is less than the degree of the bottom, for instance, let's say we've got x to the 4th over x to the 5th, where the degree of the top is less than the degree of the bottom, then the horizontal asymptote is y equals 0. If the degree of the top is bigger, like let's say we got x to the 5th over x to the 4th, then there is no horizontal asymptote. We have no parallel line. We have no horizontal line we have to worry about. And then if they're equal, like if you have got, well, we'll look at this in just a second, but you know, if it's x squared over x squared, then we're going to take the leading coefficient of the numerator divided by the leading coefficient of the denominator. None of this is hard. This is super easy, but you throw 3 different ways of looking at it together, and you're going to be using your notes. These are going to be hard for you to memorize. You'll get there. You might have to practice it a little bit. Okay, let's look at how we're going to play that. Yes, Austin, it is on my slide, on my spring slide where it says 3.5 worksheet. It's the first worksheet. So I'm always giving you these worksheets. It's just the first of this whole stack.
Can you move back to the worksheet you just pulled up? I need to write some of this down because my copier didn't put it on there for some reason.
I missed the last part of that, Kaylina. So this is what you want to look at?
Yes. The ends of like 2 of the sentences, when I printed it out, it didn't print it out for some reason.
Oh, okay.
Thank you.
You're good. Thank you. Okay, let's look at horizontal asymptotes. Let's look. We've got an 18x. Okay, and you're good, Hugh? You've got it? Great. Okay, so horizontal asymptotes, HAs. We are looking at the highest degree. There's a 1 right there. There's a 2 right there. So this is bottom heavy. Let's go research this. If the degree of the top is less than the degree of the bottom, as this one is, the degree of the top is less than the degree of the bottom, it's bottom heavy, then we have a horizontal asymptote of y equals 0. So the horizontal let's see, top is less than bottom here. So our horizontal asymptote is y equals 0. So that would tell us that we are going to have a y equals 0 line where we can have partying going on here, we can have partying going on down there, but nobody can go upstairs, nobody can go downstairs. They're going to have to keep separate there. Let's look at our second one. Here they're equal to each other. The top equals the bottom. And so that tells me that the horizontal asymptote, when they're equal to each other, will be the leading coefficient of the top divided by the leading coefficient of the bottom. So I'm going to do y equals 12 over 4, which is 3. So y equals 3 is the horizontal asymptote. So where is 3? Right about here. Y equals 3. So stuff can happen up top on this particular problem. Stuff can happen down below on this particular problem, but they can't go across that line. And then here we've got top heavy. The top is greater than the bottom. And when you've got that, you've got no horizontal asymptote. So on a graph, people can just go all over the place. Freedom to move around. We'll play with those again. And I'll bring the sheet back in too so we can remind ourselves of what's going on. Okay, 4, 5, and 6 are transformations. You are an expert on transformations at this point. Let me remind you, way back in the day, 2.5, I gave you this, put it on the slide, on the Google slide. We covered all of these, cube root, there's a snake in the grass, there's the arm, shoulder. We didn't get to these, and I told you we'd pick these up later. Later is now. 1 over x looks like these 2 boomerangs, one in the first quadrant, one in the third quadrant. X squared is the same thing except square all these negative numbers and they land up top. So we're going to have a boomerang in the first quadrant and the boomerang in the second quadrant. Nothing happening down here. We're not going to get super intense on these. Very, very basic transformations on those last two. Let's look at them. F of x, what's shown right here with little arrows, is 1 over x. We want to transform it based on g of x. And so we're from that point and that point. I just froze, didn't I? I hope it's back to normal now.
Yes, you froze. We can
Okay.
see it, but we can't see you moving. Oh, never mind, I see you moving now.
Yeah, it just takes just a second. I don't know what causes it, but we're back. Okay. That I never freeze in class. So I can't wait to get back face to face because I won't freeze in class. Okay, let's look at this. So we're going to talk about that being that boomerang's vertex point and this one being his vertex point and where we're going to move them. Look at the two things that we're going to do. This is part of the x, so we're going to do the opposite of that. X, you know, is shifting on the x-axis. It's a horizontal shift. So if it says -2, we're going to go 2 to the right. And then that number out there tells us about a vertical shift. It says +3. We're always going to do the same as what it says. So 3 up. So our new boomerangs, our g of x, is going to be 2 to the right. I'm going to take this piece right here and go boom, boom, 2 to the right, and then 3 up. 1, 2, 3. There's my new boomerang belly button. And so see how this stays in his lane, bruh? See how that happens? And this stays in his lane. He doesn't cross over to the next unit. Same thing here. Just keep him inside of that line. Keep him inside of that line. And there's the new 1 over x transferred. Let's do the same thing with this guy. There's his belly button, this part of the boomerang. Let's go 2 to the right, 1, 2, and then up 3, 1, 2, 3. And then look at what his shape's going to be like. So we're going to stay in his lane again, right there. He'll continue going out here, but he'll never get to that line. And then he'll go down here, getting closer and closer and closer to that unit, but never crossing that line. He stays on the path. He stays in that sidewalk. So we just move these over, 2 to the right and 3 up. Okay, let's look at the x squareds. You know that the x squareds are boomerangs that are both on the top half of the graph. We're going to transform them g of x, x plus 3 squared. So you know that this is going to be the opposite. It's only got one change. There's no number sitting out here. So we're just going to go 3 to the left here. Remember, you're doing the opposite of a +3. So I'm going to take that belly button right there, and I'm going to shift him 1, 2, 3 to the left. Here's where his new belly button is. Keep him on this path. Don't let him cross a line. Goes up there, comes down here, does that same sort of thing. That's kind of Richardy, something like that. Okay, same thing here. That meant to be a black one. Same thing here. This belly button of the boomerang on the right-hand side is going to go 3 to the left also. So 1, 2, 3, he'll sit right here. And again, we're just duplicating it. We just moved him over a little bit, like that. Okay, just because we need to talk about this, you can see there's a horizontal asymptote right there. This line, as it goes out to infinity on the x-axis, it gets closer and closer and closer and closer and closer to 0 on the y. So this arm of it, as it goes out to infinity, is getting closer and closer and closer to 0. This arm right here, there's a horizontal, there's a vertical asymptote going on here too that they're not crossing. As this arm right here on the x, it gets closer and closer and closer to -3. As it gets closer and closer to the x of -3, it's getting closer and closer and closer to the y of infinity. And we'll talk about that again when it's more important. But we got all kinds of asymptotes going on in there. Let's do this one. Same thing. It's the 2 that go up. We're going to change it. There's no opposite thing going on here. There is no number attached to the x, so we're not shifting it sideways. We are only shifting it there, and that is down 1. -1 on the vertical. So this guy's belly button is right there. I'm going to shift him down 1 to right here. He's going to stay in his lane. Like that. Same thing's going on with this guy. There's sort of his armpit. I don't know. What do boomerangs have? They probably don't have armpits. Go up here and then down here. You'll be matching on all of these. You won't have to draw them. They don't have a little figure for you to grab. You'll just be matching, which I'm sure makes a lot of you pretty happy. Okay, let's move to the next page. 7, 8, 9, and 10 will all be graphs from start to finish. We are going to graph these based on all of the steps that we've been looking at. Oh, and plus a few more. Let's see. Here's the set of things we're going to look at. I'm going to go through them with you. Number 1 is vertical asymptotes. Do we have vertical asymptotes? Set the denominator equal to 0 to find those. That's where this cannot go, and that's always going to be found in the denominator. So it's got a vertical asymptote of x equals 2. We're going to have to avoid that right there. We're not going to be able to cross that line. We will not have any of our figure doing anything across that line. Horizontal asymptote is next. Horizontal asymptote are those 3 rules. And then that says slant asymptote. We're only looking at slant asymptote on the last one, so we won't worry about that in each of these. But horizontal asymptote, let's look at our 3 rules. Talks about if the degree of the top and the degree of the bottom, let's look what we've got. They match there. Oh, I changed this problem. Let me change this to a 4. I changed that. If you copied this down, or sorry, if you printed it out, you've got a 4 right there because it fits better on the graph. So we've got a 4 up there. If the degree of the top, how does it compare to the degree on the bottom? They're the same. So if the degree of the top equals the degree of the bottom, then the horizontal asymptote will be y equals the leading coefficient of the top over the bottom. So our horizontal asymptote here is going to be y equals 4 over 1, the leading coefficient of the top over the leading coefficient of the bottom, which gives us 4. So y equals 4 is our horizontal asymptote. Let me draw that in right there. We're not going to be able to go much. This is y equals 2, or x equals 2. So we're going to have to stay, if we start something over here, it's going to have to stay over here. If we start something here, it's going to have to stay there. Let's keep moving. Next thing we're looking at is x-intercepts. Does our guy cross the x-axis anywhere? To find x-intercepts, oh, that's weird. You set the numerator to 0. So let's set the numerator equal to 0. That gives us x equals 0. That's the x-intercept, setting the numerator to 0. So that means our graph is going to cross the x-axis at 0. There's a good point for us. We know that somehow or another that point is involved in this graph. Number 4 is looking at the y-intercept. The y-intercept, in order to find the y-intercept, we're going to do f of 0. Remember, anytime you're looking for the intercept, you 0 out the other guy, and the other guy's an x. So plug in a 0. We're going to get 4 times 0 over 0 minus 2. That gives us 0 over -2, which is 0. So the y-intercept, where this crosses the y-axis, we already knew that. Bummer. No new information there. Number 5 is additional points. Let's look and see if we're going to have to find some points. I mean, look at this. We got 1 point. So how are we going to do that? Super easy. Let's grab, let's see, this is a over x. This is not an x squared. This is an x graph. So we know it's boomerangy, and we know one's going to be in one corner and the other's going to be in the opposite corner. I don't see any negative x's. So well, I've got a point down here. That's more to the point. So I know we're going to do a boomerang here. And if we're doing a boomerang here, we're going to do a boomerang up here. So let's discover what those points are. Don't worry about 0, 0. We've got him. Let's pull way over here to -5. We're going to expect something like this. So let's look and see what happens over here at -5. If you plug in a -5 into the equation, you'll get 4 times -5 over -5 minus 2. That's -20 over -7. That's about 3. That's almost 3. 21 over 7 would be 3. So it's close enough for us. So -5, +3. -5, +3, right there. Okay, that's starting to look like a boomerang. I can see that it's going to do this sort of thing. Let's check out what happens down here. Let's look at what happens over 1 minus 2. That gives us 4 over -1, which gives us -4. So 1, -4. Okay, that's good enough for me. Let's draw that boomerang in. Like that. Oh, don't know where I lost you, Austin, but I'm plugging numbers in. I've got -5 there at the 1. Okay, so I'm trying 1. I just plugged a 1 in. 4 times 1 will give me 4. 1 minus 2, x minus 2 gives me -1. That's a -4. So 1 -4, and sure enough, that's looking like a boomerang. So we're good. We're good there. We also know that it's going to happen up here because we know that the 1 over x, good. We also know something's going to have to happen over here. So let's look at where those x's are. That's like 3, 4, 5, 6, 7. That's going to happen over there. Rebecca, let's see. Plugging it in, I'm getting 4 times 1, so that's a 4 on top. And on bottom, it's 1 minus 2, so that's a -1. So that'll give me a -4 right there. It's not a 2, it's 1 minus 2, not 0 minus 2. Oh, multiplied, okay. Okay, yeah, I can see that. So it's just subtract. Okay, so let's see what's happening. This boomerang is happening this way. I'm expecting a boomerang like that up here. So you can grab 3 or 4 or 5 or 6. I would expect 3 to be up here, and then 4, and then 5, and then 6. It's the reflection of that. So let's just grab 3 and see what happens. 4 times 3 over 3 minus 2, that gives us 12 over 1, which is 12. So let's graph 3, 12. Go out 3, go up 12. It's off the piece of paper. It's way up there. Exactly what we were expecting. We want this to happen here. Let's check 5. And I'm just picking numbers. These are, it's just what I'm expecting a boomerang to do. So I've got 4 times 5 over 5 minus 2. That's 20 over 3, 7-ish. So let's do 5, go out 5, go up 7. And then if we check 6, 6 times 4 over 6 minus 2, I get 24 over 4, which is 6. So 6, 6, go out 6 and up 6. And there, that's that boomerang happening. Something like that. It'll get closer and closer and closer to this line that is y equals 4 as it goes out there, but it won't quite touch. This one is going to, as it goes up, will continue to go up, but it can't touch this blue line. It can't touch our horizontal asymptote. How about vertical? It can't touch our vertical asymptote. It's going to get closer and closer and closer. So let's look at this. This is a good question for what I'm doing right now, playing with these. We have 4 different arms. They're going to ask you a question about one of the arms. This asks you, as x approaches 2 from the negative direction. So as x approaches 2 from the negative direction, that means from over here as we get closer and closer to x. Okay, so that's asking us about this boomerang, not that one, because this one does not approach 2 from the negative. It approaches 2 from the positive direction. So we're being asked about this boomerang. As x approaches 2, as it gets closer and closer to 2, okay, we can see we're talking about this arm. So what is happening on the y-axis as this orange gets closer and closer and closer to 2? it gets further and further on down. What's happening to the y? What is this one trying to do? He's trying to go down to negative infinity. So that's negative infinity right there. As x approaches 2 from the negative direction, there's a little negative sign right there. As x starts being 2 from the negative, what's happening to the y? What is this function doing on the y-axis? It's tubing. It's going to negative infinity. And the last thing we're looking at here, number 6, is symmetry. Well, look at this. This does not have this does not have y-axis symmetry. This is not down the middle right here. And it does not have origin symmetry. So if we spin this arm around, it's going to stick up there somewhere. The way to tell that is to look at f of negative x. If we plug in a negative x here, we'll get 4 times negative x over negative x minus 2. That'll give us negative 4x over x minus 2. Let's look. Is this the same that we started with, or is this the opposite? Well, the negative is the opposite on the numerator. Then that x to a negative x, that's cool. That's an opposite. Oh, the negative 2 didn't turn to anything. So there is no symmetry here. And you can look at that and see that that does not look like a person, left hand matching the right hand. And it does not look like if you spun it 180 degrees. Okay, we are done with number 7. Let's move to number 8, doing the same kind of thing in these 6 steps. Vertical asymptote first. Vertical asymptote means you're setting the denominator equal to 0. So we'll factor this. The signs need to be different. I need 2 numbers that will multiply to 20, whose difference is 1. That's 4 and 5. And if I want these 2 added together to give me a positive 1, I need that to be the positive, and I need the 4 to be the negative. So I'll put the 4 there and the 5 there. That gives me 2 vertical asymptotes, x equals negative 5 and x equals 4. So let's draw those asymptotes in there. It's really kind of fun to say because you can kind of almost say a dirty word. Let's see, negative 5 is right here. And 4 is right here. Now, if our 2 walls were in the same place, like at negative 5 and 5, or at 4 and negative 4, then we might have a possibility of having some symmetry. But they're just barely off. You know, like your eyebrows aren't quite symmetrical to each other. Same thing happening here. So this will not be symmetrical because we're setting up walls that aren't even symmetrical to each other. Just FYI. Number 2, horizontal asymptote. Remember, that looks at the degree. Okay, we've got no degree up here. No degree there, 2 degree there. So we have got a top that is less than the bottom. And so to remind you, when your top is less than the degree of the bottom, your asymptote is y equals 0. So y equals 0 will be our only, and you'll only have one, our only horizontal asymptote running through here. So let's see, that breaks our entire grid up into 1, 2, 3, 4, 5, 6 parts. We're going to cover some of them. We just don't know which ones yet. Number 3, looking for x-intercepts. We're looking for where we cross the x-axis. Well, look at that. We can't cross the x-axis. We can't even sit on the x-axis. This is telling us we're not allowed to use the x-axis at all. So we're not going to find any, but I want to go through this process so you can see how that'll look to you. Set the numerator equal to 0 to find x-intercepts. So 8 equals 0, and that makes absolutely no sense to us. So we have no x-intercepts. A number cannot equal, a non-zero number cannot equal 0, which makes sense because we got to stay off of that line. Y-intercept. To find the y-intercept, you 0 out the other guy, 0 out the x. So let's put a 0 in for x. That'll be an 8 still on top. 0 plus 0 minus 20. So let me change that to a decimal, and we're getting negative 0.4. So negative 0.4 on the y-axis. There's the y-axis. This is 0. That's negative 1. Negative 0.4. It's right around halfway. Next thing is additional points. We don't know what's going on here. I see an x squared at the bottom. That tells me that I'm going to have 2 boomerangs in the top half of the, above this horizontal asymptote. I'm going to have 2 boomerangs. And I know because there's a certain amount of symmetry, they're going to be sitting here. I know that. You don't know that. But let's find out how we can figure that out. Okay. Something's going on in here because there's a point down there. So I know that it's not going to happen. This block will be left open because there's no way for this point to get up there. So we're not going to have anything happening up here. If you've got a horizontal asymptote, you can be guaranteed that if you got something down here, nothing's happening up there. So let's discover what's happening down here. Let's grab negative 4. See what happens there. So that'll be 8 divided by 16 minus 4 minus 20. 16 minus 4 is 12. 12 minus 20 is negative 8. We get a negative 1 there. So negative 4, negative 1. That didn't help us a whole lot. I mean, I can see it, arcing there. Let's go over here and see what's happening at 3. See what's going on at 3. So 8 over 9 plus 3 minus 20. 9 plus 3 is 12. 12 minus 20 is negative 8. There's that little bit of symmetry that it does have. It has some symmetry, and that's 3, negative 1. But its symmetry is kind of shifted over a little bit. This will not be the center point. The center point, the topmost, must be just to the left here. I don't care enough about to look for it. But I want to make sure it's going to drop down here. So I can either check negative 4.9 right on the edge or positive 3.9. And I want to check positive because positives are more fun than negatives. So I'm going to put 3.9 in here. So I'm going to get 8 over 3.9 squared is 1521 plus 3.9 minus 20 gives me 8 over negative 0.89, which ends up being very close to negative 9. Okay, now I can see what's happening. 3.9, very close to the asymptote, negative 9. So down here, even further than that. So this is going to be doing, oops, missed it, that kind of thing. So that doesn't really look like a boomerang, sort of does. It's a stretched out boomerang, but we'll take it. Now let's find out what's happening on the outsides of our 2 vertical asymptotes. Let's grab 5 and see what's happening there. If you put in a 5, 8 over 25 plus 5 minus 20 gives us 8 over 10, just gives us 4. So 5, go out 5, go up 0.4. So something like that. How about 0.8? 8 over 10, 8 tenths, 8 tenths. So I kind of got it a little bit low, but that's okay. Make it a bigger blob. And that's going to be a boomerang. If you're not sure, let's grab something else. Let's grab 7. Let's just see what's happening at 7. 8 over 49 plus 7 minus 20. That gives us 56. Minus 20 is 36. That is, let's just reduce it. 4 over 18, 2 over 9, 2/9. So just barely. So 7, go out to 7, barely up, 2/9. So this is going to do that kind of thing. And we know we'll have the similar reflected thing going on here. So there you go. You can just draw that. You can assume symmetry, a certain amount of symmetry around these. Okay. Of course, the only one that I really bombed on this was the one I want to look at with you. Oh, let's do this first. Number 6, symmetry. put in negative x. So f of negative x will give us 8 over negative x squared will give us x squared. Negative x will give us negative x minus 20. So the 8 stays the same. The x squared stays the same. Oh, that one changed signs. So there's no symmetry here. No symmetry. It has to either stay exactly the same or everybody has to change to its opposite signs. Okay, let's look at this as one. As x approaches negative infinity. Okay, you know where negative infinity is. It's way over here on the left. And as we've got how many arms here? 1, 2, 3, 4, 5, 6. They happen to be talking about this arm right here because that's the only place where x approaches negative infinity. So they're giving us what's happening on the x. The x is going way out here to negative infinity. They're asking you what's happening to the y. What are we getting close to on the y? Well, we've got this asymptote here. So on the on the thermometer, as we go zooming out here, we're getting closer and closer and closer to 0, but not quite getting to it. So the arm they're asking you about is this arm. They're telling you what the x is doing. It's going out there to negative infinity. You're telling them what the y is doing. What are you getting close to on the y-axis? There's the y-axis. It's the thermometer. You're getting close to 0, but you're not going to cross it. We'll play with those some more, those as things. Let's look at number 9. Okay, same list. I changed this one to x minus 4 and x squared minus 16, so it would stay on the graph. I've changed it now permanently, so I had this printed up before. Vertical asymptote is first. We're setting the denominator equal to 0. So let's factor the denominator, x plus 4, x minus 4. We end up with vertical asymptotes. Oh, hang on a second. Before we do that, I'm seeing that we're getting x minus 4 there. That means this will factor and cancel. So we have an x minus 4 on top. This, when we factor it, gives us x plus 4, x minus 4. The x minus 4's cancel, and we're left with 1 over x plus 4. So what that tells us is that we've got one vertical asymptote at x equals negative 4. There's our vertical asymptote. The other thing it tells us, back over here, we canceled out the x minus 4, but that's a hole. We're going to have with a hole at x equals 4. We're going to have a hole right there that we're not going to be able to have a number at. Because if you put in 4 for the x back here, 4 squared is 16, 16 minus 16, kablooey. So we're going to have a hole right there. I won't forget that when we get there. Okay. I think that's all we have to worry about there. Number 2, horizontal asymptotes. We got that set of rules. Go back to the original. It's bottom heavy. So when the degree on top is less than the degree of the bottom, then the horizontal asymptote is x equals 0. So, sorry, y equals 0. Y equals 0. Let's set up another asymptote here. Okay. Before we get too far, let's back up and look at what we've simplified this to be. 1 over x plus 4. Remember back, hang on. Let me go back there. Here it is. When we were transforming these, 1 over x looks like those two boomerangs, and we only have one transformation happening here. It's at plus 4. That's a liar, so we need to scoot ourselves back 4, just like this is doing. So we're going to end up with a boomerang there and a boomerang here, just shifted from their normal places of hanging on to the 1, 1 and the negative 1, negative 1. They're just scooting over 4 places. I don't expect you to be on top of this completely and be comfortable with that. I just wanted to show you that. Let's keep moving. X-intercepts. This cannot cross the x-axis. That's got a barrier right there, but let's see how it'll happen. Set the numerator equal to 0. So x minus 4 equals 0. We get x equals 4, but we've already found we've got a hole at x equals 4, so we're not going to have an x-intercept. Number 4, we're looking for where does this cross the y-axis. In order to find that, do f of 0. So I've got 0 minus 4 over 0 squared minus 16. That'll give me a negative 4 over negative 16, which is 1/4. So the y-intercept here is at y equals 1/4. Let's see. There's the y-axis. 1/4 is way down there. And we're going to cross that place. I'm going to do something like that right in there. Let's look at additional points. Okay, I'm thinking this needs to go way up here. Let's try what's happening at negative 3. So negative 3 minus 4 is the numerator, and then negative 3 squared minus 16. So I get negative 7 over negative 7, I get a positive 1. So negative 3, positive 1 is right here. That's heading up right there. If we did negative 3.9, something like that, almost to negative 4, we'd find out that it's way up here. Let's go beyond that. Let's we know what this is happening here. So we're going to boomerang this in. Let's go look at what's happening over here. Let's look at negative 5. That'll be negative 5 minus 4 on top, and then negative 5 squared is 25 minus 16 is the denominator. We get negative 9 over a positive 9. It gives us a negative 1. So we've got negative 5, negative 1. You know these are going to be symmetrical to one another. But, you know, if you want to test it, you can. But you know what this is going to look like. It's got to be boomerangs in alternating quadrants. It was just 2 boomerangs scooted over 4. Staying in its lane, staying in its lane, staying in the lane, staying in the lane. The symmetry of it, there is no y-axis or x-axis symmetry. There is symmetry along this thing, but that's not what this is asking for. So if we do f of negative x, we get negative x minus 4. Negative x squared will give us x squared. Let's see now what we've got. Negative changed its sign, but the negative 4 didn't change its sign. The x squared didn't change it. Since we've got a hodgepodge here, there is no good symmetry. There's no y-axis or origin symmetry. And let's look at which arm they're talking about. We have 4 hands here, 4 ends of our boomerang. They're asking you about one of them. As x goes to infinity, so go along the x-axis toward infinity. Here's the x-axis. We're not going that way. That's negative infinity. We're going this way. So we're looking at this arm right here and asking ourselves what's happening there. They're telling us that as this goes out, the x number will get to be infinite. 6, 7, 8, 9, on out to infinity. They want to know what's happening to the y. What is happening along the y-axis? What is it getting close to? It is approaching. That's what that arrow tells you. It's approaching. It's getting closer and closer to 0 on the y-axis. So it is approaching 0. Let's do another one down here because I've looked at the homework. Apparently not enough for everything, but I've looked at a bit of the homework. Let's say that we have got a horizontal asymptote at y equals negative 4 there. That's our horizontal asymptote, obviously. And let's say our graph looks like that. So we've also, you can tell, got a vertical asymptote. Let me extend this down here. We've also got a vertical asymptote going on of x equals 0. Okay, let's say that the question is, as x approaches negative infinity, f of x approaches what number? That's what we're looking at. So we have two arms here, two hands here. We're trying to figure out which one they're asking us about. As x goes to negative infinity. So x goes to negative, here's the x-axis, as it goes to negative infinity. So we're talking about this hand right here. They're asking you what is happening on the y-axis. What is this orange guy? What is this guy getting closer and closer to? As he heads out here, he's getting closer and closer on the y-axis to that -4 line. So that would be a -4 right there. If they had asked you, as x approaches, let's see what this is doing. The x is approaching 0 here. It's approaching 0 from the negative side. That should go on the other side. As x is approaching 0 from the negative side, f of x is approaching. Okay, so as x is approaching 0 from the negative, oh, here it goes. So this is getting closer and closer and closer to 0. What's happening to the y? Where are we going on the y? We're going to negative infinity. We're going way down there on the y-axis on the thermometer. Okay, let's get a little bitty teeny weeny ways into this one so that we match what we did with the other class. We're not going to finish it. It'll take about a minute. Let's see. Nah, let's wait on it. That would make more sense because then we can do the complete problem on Wednesday. So where are we besides done? We are looking at, we've done 3-6A. Told you at the very, very, very beginning of today, I would appreciate it if you could, you would appreciate it if you do those 6 problems on 3.6A before Wednesday, because then 3.6B will make a whole lot more sense to you. If you feel like putting 3.5 off, put it off. I mean, after this Friday, after this Wednesday, really, you've got a whole week, you've got spring break off. And I am going to open up all of my math lab, all of Unit 1 and all of Unit 2, for the half of you or so that don't have hundreds all the way across. You don't have to do that. If you've got something better you'd like to do, that's fine. But those of you who don't have A's on my math lab, boy, I wish you'd spend that time. It will be worth your while, I promise. So I think we're done. We'll come back and finish up that last problem and do 3.6B. Not there yet, Giovanni, not there yet. One more day for this class, and I don't know what else you got going, but it's coming up fast. Okay, so stick around if you have a question. Otherwise, I'll see you on Wednesday. Try to get those 6 problems done on 3.6A by Wednesday, and have a good couple of days. You are welcome, all y'all. Yes, Jackie, the extra points have already been added, so you can see what your grade was on the test. You can go look it over, and then I added in your extra points to that grade. If you have any question about that, I'd be happy to talk about yours specifically.
So if the extra points were added already, I'm assuming you docked me 8 points because my grade didn't change from what it was on the test.
That would be a bad assumption, wouldn't it? Let me check. Let me look at what I got here.
Because on the original test, I got a 98 and it didn't change, and you said you added the points. I never got a
98. 98 isn't a grade you could make on that test because each one counted 4 points. So let's see.
92. Sorry, 92.
92. Okay.
Yeah.
Crap. What is your last name, Helena?
Dunn. D-U-N-N.
Okay. Yeah, wow, yeah.
Because I remember whenever I emailed you my scratch paper, I never got an email back from you.
I didn't get you. Oh, your scratch work. Yeah, I don't. If there was no problem, I wouldn't have emailed you back if there was no problem on this one. I am looking, because you go under a different name. There you are. You're up at the top under the A. Okay.
So
I've got 100 written there. Let me check. Oh, and I'm going to freeze. If I go away, you know what? I can talk. That's not going to be a problem. So let me go down to the grade center and check. Helena is up there. Got 100 there. I got 100 recorded for you. Are you looking under test 2 or are you looking under test 1?
I was looking under test 2 and it said that it was a 92.
Now way out at at the one that says proctored, it will say that. But you need to look under the test 2 where the grades are. So you somewhere else in that list, you should have a test 2 that is 100.
I see, okay.
And that 92 will completely go away. I just have to hold on to it for a couple more days because of a student that is going to take it late. But you should have 100. So yes, I did not. I'm not screwing you over, Kaylina. I want you to win this game.
I got the wrong section. Okay.
Okay. Good deal.
Thank you for clearing that
You're
up.
welcome. Yeah.
And I froze. I can't leave.
I froze too, and I put in a couple of questions about that. So, and I don't know what tech support's going to do. I'm not sure why you froze, but teachers keep freezing on this silly BBCU, and we complain about it, but I don't know.
Now I'm pretty sure the only way I can get out of this is if I turn off my computer or close Google.
That'll do it. That's a surefire way, isn't it?
Bye bye.
Bye.